Imagine standing in the center of just this impossibly massive, totally chaotic library.
Oh, sounds like a nightmare, honestly.
Right. Like you look around and you see millions upon millions of books just piled up to the ceiling in random stacks. And, well, it isn't just books, actually. It's authors, publishers, translators, and like millions of tiny slips of paper with reader reviews scribbled on them, just fluttering around in this literal tornado of information.
It's absolute chaos.
Total chaos. Now imagine someone walks up to you and says, I need you to instantly find every exact connection between all of these pieces of paper right now.
Yeah, good luck with that.
I mean, it sounds like an absolute nightmare. But what if I told you there's an invisible blueprint handling this exact kind of chaos on your phone right now, literally millions of times a second?
It's kind of wild to think about.
It really is. So welcome to the Deep Dive. Today, we're cracking open the architecture that actually solves this exact problem, which is relational databases and SQL. We're going to unpack how information isn't just stored in our modern world, but like how it's structurally related.
Yeah, it really is the invisible scaffolding of the modern world. And looking at the source material we're diving into today, which comes from a computer science lecture on databases, and SQL relating what's really fascinating is the visual journey we get to take.
Oh, for sure.
Because we're actually going to start in that massive, dusty library of books you just described. But by the end of this, the backdrop is going to shift entirely.
Wait, where are we going?
We'll actually be looking at a map of the Pacific coast, tracking the dynamic migration patterns of sea lions.
Oh, wow. Sea lions. I love that.
Right. It's a brilliant way to see how these underlying principles apply to literally any type of data, whether it's, static text sitting on a shelf or wild animals moving through the ocean.
Okay, so from dusty bookshelves to the open ocean, I am ready. But let's start at the very beginning, in that chaotic library. If we're looking at this giant pile of books and authors, what is the literal first step? Because my instinct is just to start sorting things alphabetically, which I feel like is probably wrong.
I mean, alphabetizing is a very human instinct, but for a database, the first step is actually, it's philosophical.
Philosophical, yeah.
Yeah, it's something called an entity relationship diagram or an ER diagram, because before you can even think about writing code or building digital tables, you have to define what things actually are and how they interact.
Right.
It's about establishing the blueprint of reality. So in our source material, they place a book entity right at the center of the diagram, just a box labeled book.
Okay, simple enough.
But a book doesn't exist in a vacuum, right? So the diagram draws lines outward to show relationships. A book has a rating. A book was written by an author. It was published by a publisher. And it might have been translated by a translator.
So we're basically drawing a map of how these distinct concepts just touch each other in the real world.
Spot on. And the crucial part is defining the type of relationship. We break these down using 3 basic concepts, which are 0, 1, and many.
Okay.
This gives us relationships like one-to-one, one-to-many, and many-to-many. Let's look at the rote relationship between an author and a book.
Sure.
Take the author Olga Tokarczuk, for example. She's one single entity, one author, but she can write many books. In our sources, we see she wrote Flights and the Books of Jacob.
Right, so one author, many books.
Exactly. So that's a one-to-many relationship. But it goes the other way, too, A single book could be written by multiple authors. So suddenly, between authors and books, you have a many-to-many relationship.
Okay, let me play devil's advocate for a second here.
Go for it.
If we're just trying to keep track of a bunch of books, why do we need all these separate conceptual boxes and lines? Like, why not just make one massive, easy-to-read Excel spreadsheet?
Ah, the giant spreadsheet.
Right. You just have a row for the book and columns that say author, publisher, translator, and so on. Let's be real. Why overcomplicate it?
It's the most common question people ask, honestly, and it's how most of us start organizing our own personal information. But if we connect this to the bigger picture, the massive spreadsheet approach, what data scientists call a flat file, it creates a catastrophic problem, which is redundancy.
Redundancy, yeah.
Yeah. Let's say Fitzcarraldo Editions, which is a publisher in our data set, decides to move their headquarters and update their address.
Okay, happens all the time.
If you have a flat spreadsheet and Fitzcarraldo has published, say, 3,000 different books, you now have to manually find and update 3,000 separate rows.
Oh, wow. Yeah, I see the issue. And if I make a typo on row 2000, the data is instantly corrupted.
Exactly. You'd have Fitzcarraldo editions in one row and like Fitzcarrall editions in another, and the computer thinks those are two totally different companies now.
Which ruins everything.
Yeah. Right. So relational databases solve this by completely separating the tables. You only store Olga Tokarczuk's name in one single place, the author's table. You only store Fitzcarraldo editions in the publisher's table.
And then they just link up.
Yes. The main books table just points to them. So if Fitzcarraldo changes their address, you update it in exactly one cell in one table. Instantly, universally, every single book connected to them is pointing to the correct updated information.
Okay, I mean, the efficiency there is undeniable, but that raises a massive logistical catch for me.
What's that?
Well, if these entities are stored in totally different tables, like if the book title is sitting over in table A and the author's name is sitting in table B, how does the system actually know which author goes with which book without getting hopelessly confused? Because human language is incredibly messy.
Oh, it's worse than messy. It's deeply ambiguous. And that brings us to the problem of names and why we desperately need keys.
Yes. The source material actually has a hilarious example of exactly how messy names can be. They look at a book by Laurent Mouvignier called The Birthday Party.
Oh, right. This is a great example.
If you just try to search a basic database using text, just searching for the title and author, you get this chaotic mess of conflicting entries. Like the sources show search results like The Birthday Party Wendy Dranfield paperback, which is a totally different thriller novel.
Right, completely different book.
Exactly. Then you have The Birthday Party Laurent Mouvignier hardcover in paperback, first edition, second edition, The Birthday Party by Laurent Mouvignier. Like, if the database is just looking at text, it has no idea if these are the same book or 10 entirely different books.
Which is exactly why you can never, ever rely on a descriptive name to link data. You need what's called a primary key.
Primary key?
Yeah, a primary key is the absolute, unquestionable truth of that entity's identity. It's a unique identifier that strips away all the messy text. In the case of books, the world has actually already provided us with a perfect primary key, which is the ISBN, the International Standard Book Number.
Oh, right. The barcode number,
Right.
basically.
Exactly. Regardless of whether the text description says first edition or hardcover or even has a typo in the author's name, the ISBN, like 978-180-427-0226 for The Birthday Party, is entirely unique.
So it's like a digital fingerprint for that specific entity. No two books on Earth share it.
Exactly. Every single book gets its unique fingerprint, its primary key.
Okay, here's where it gets really interesting to me, though. How do we attach outside information to that fingerprint? For example, how do we attach reader reviews? Because a review isn't part of the book itself.
To do that, we introduce the concept of a foreign key. This is the actual mechanism of how tables talk to each other.
Okay, break that down for me.
Let's look at the book Boulder by Eva Baltazar. Its ISBN is 978-8439736967. If a reader gives it a 4-star review, the database doesn't go into the main books table and physically write, got a 4 next to the title.
Because that would mess up our clean table.
Right. Instead, there's a completely separate ratings table. And in that ratings table, we simply list the ISBN, or, even more efficiently, a simple internal book ID, like the number 1 right next to the rating of 4.
So the ID is the link.
Yes, that book ID is acting as a foreign key. It's a key native to the books table, just taking a little vacation over in the ratings table to act as a reference point.
Wait, I'm trying to picture this. So if the ratings table doesn't have the book title, or the author, or the publisher, it's literally just a giant list of meaningless numbers unless you have the key to translate it.
That's right. The ratings table doesn't know anything about Eva Baltazar. It just holds the foreign key and the score.
Wow.
Yeah, the source shows exactly this. Book ID 74, which happens to be the White Book by Han Kang, just has a row with a 2 and another row with a 3 in the ratings table.
You know, it's wild to think about this in the context of daily life. Like every single time you leave a star rating on a shopping app or, a restaurant delivery service, you aren't actually modifying the products page. You are literally just dropping a foreign key and a number into a massive invisible bucket somewhere on a server in another time zone.
Yep. Millions of times a second, all over the world, we are just generating foreign keys.
Okay, so the data is incredibly secure. It's locked into these pristine, separate tables with zero redundancy. But now we have the opposite problem.
Which is?
If everything is fractured and hidden behind these numeric keys, how do we actually get the information back out? Like when we want to ask a complex question, how do we stitch it back together?
This is where we start interrogating the system using SQL, which stands for Structured Query Language. And when a question gets complex, we use something called subqueries.
Subqueries. Okay.
The logic here is really fascinating because sometimes you simply cannot get your answer in one single step. You have to ask the database to figure something out first before it can even understand your main question.
Right. I've heard this compared to digital matryoshka dolls, like those Russian nesting dolls.
Yeah.
You're putting one question inside of another. You hand a sealed envelope to the database, and inside that envelope is another sealed envelope that it has to open and solve first.
That's a really good analogy, but let's push it a bit further. The reason it's like a sealed envelope is because the database engine literally cannot see the outer shell's logic until the inner doll is fully unpacked and evaluated into a hard number.
It can't just guess what you mean.
Exactly. It lacks the ability to just guess the string of text. Let's take the publisher example from the sources. Suppose you want to find all the book titles published by Fitzcarraldo Editions. But the books table only has a numeric publisher ID column, right? It doesn't contain the word Fitzcarraldo.
So I can't just ask the books table directly. It won't know what I'm talking about.
Right. First, you have to run an inner query. In SQL, you literally speak to the database in simple verbs. You tell it to select the ID number from the publisher's table, where the name is Fitzcarraldo Editions.
Okay.
The database runs that inner query, opens the envelope, and finds the ID number 5.
Okay, so now it has a 5. What does it do with it?
It feeds that 5 directly into the outer query. Now you're telling it to select the title from the books table where the publisher ID is 5, and boom, it returns the titles, minor detail, and paradise. You asked one conceptual question, but the system had to run 2 sequential queries to get there.
And you can nest these really deep, right? Like the sources showed a 3-level subquery that felt like a full-blown detective hunt just to find the name of the author who wrote Flights.
Yes, that's a perfect example of navigating a many-to-many relationship because authors and books are connected by a separate linking table called authored.
Oh, right. Because a book can have many authors.
Exactly. So to find who wrote Flights, we have 3 steps. Step 1, the innermost query. You tell the database to find the book ID for the title Flights. It comes back with ID 78.
Got it.
Step 2, the middle query. You look in the authored linking table to find the author ID associated with the book ID 78. It evaluates that and returns ID 58.
We are so deep in the envelopes right now.
Almost there. Finally, step 3, the outermost query. You look up author ID 58 in the author's table to get the actual text name, which is Olga Tokarczuk.
Wow. It traces the breadcrumbs through 3 different tables automatically.
Eh.
I also noticed the sources note that sometimes these inner queries return more than just one ID. Like if you ask for all books published by Yale University Press, you might get a whole list of IDs back. How does the outer query handle that without breaking?
That's where the SQL command ANN comes in. Instead of saying where the ID equals 5, you say where the ID is in this list I just generated.
Oh, that makes sense.
Yeah, it gives the database the flexibility to handle multiple answers from a subquery seamlessly.
Okay, I see why subqueries are amazing for these very specific, targeted sniper hunts, finding one author, finding the books of one publisher. But what if we're not hunting for one specific thing? What if we want to look at a massive, combined view of 2 tables at once? And what if the data isn't just dusty books sitting statically on a shelf, but something messy and moving?
To explore that, we need to completely shift our scenery. We're leaving the library behind.
Yes. Okay, so shifting the visual from the bookshelves. Imagine a map of the Pacific Northwest coast. And right next to it, a photo of a sea lion looking up at the sky.
Sea lions.
Yes, we are looking at actual sea lion migration data.
It's a brilliant data set to illustrate our next major concept, which is JOANs. We have 2 entirely different tables here. Table 1 is our identities table. It has the sea lions' internal database IDs and their given names.
Who are our sea lions?
We have Aya with ID 10484, Spot at 11728, Tiger at 11729, Mabel at 11732, Rick at 11734, and Jolie at 11790.
I just have to say those are top-tier sea lion
They
names.
really are. Now, table 2 is the migrations table. This data comes from their tracking collars. It has IDs, distance traveled, and days at sea. So we see ID 10484 went 1,000 miles in 107 days. ID 11728 went 1,531 miles in 56 days, and so on.
So we have the names isolated over here and the distance is isolated over there. How do we fuse them together to see the whole picture?
We use joins. A join tells the database to stitch these 2 tables side by side based on their matching IDs. But there are very strict rules for how that stitching happens. The most common rule is the inner join.
Okay, an inner join. I like to think of this as a very strict VIP party bouncer.
I like that. Walk me through it.
Well, the bouncer is standing at the door with two lists, the identities list and the migrations list. If you are a sea lion
Mm,
and you want to get into the inner join party, you have to be on both lists. If you aren't on both, you aren't getting in.
perfect analogy.
Right. So Aya and Spot, they're on both. They walk right in and we can see their names and their distances right next to each other.
Right.
But Jolie. Jolie has a name, but for some reason she has no migration data from a caller. The bouncer turns her away.
Sadly, yes.
And then there's this mysterious ID 11735 in the tracking data. They migrated 2,723 miles in 82 days, a massive journey, but they have no name registered in our system. So the bouncer turns them away too.
That is a highly accurate way to look at it. An inner join only returns the perfect, pristine overlaps. But, as an analyst or a marine biologist, you don't always want to ignore the missing data.
Because sometimes the missing data is the story.
Exactly. Why didn't Jolie's collar work? Who is this mystery sea lion traveling almost 3,000 miles? If we want to see them, we have to use outer joins.
Wait, so if I want everyone, even the ones missing data, do I just tell the bouncer to tear up the guest list entirely?
Not exactly tear it up, but you change their instructions. We have three types of outer joins. First, the left outer join. This tells the database, keep absolutely everyone from the left-hand table, in this case, the names table, and bring in whatever migration data you can find to match.
So Jolie gets into the party this time.
She does, but because she has no tracking data, her distance and days columns just say NL.
I want to pause on NL for a second because I feel like it's an important concept. NL doesn't mean zero, right?
Exactly right. It's not that the value is zero. Zero is an actual number. You can travel 0 miles. NLL means the database literally shrugs its shoulders. It's a void. It's the database equivalent of I don't know or data does not exist.
So Jolie gets in, but her name tag has a literal void for her distance.
Precisely. Then there's the right outer join. This does the exact reverse. It says keep all the migration data from the right-hand table and bring in whatever names you can find.
So now our mystery sea lion, ID 11535, gets in. We see their massive 2723 route journey, but under the name column, we just get that NLL void.
Yep.
Okay, but what if I really do want everyone? Like, I don't care if they have an NL name or NL distance. I just want the whole messy picture.
Then you use the full outer join. It throws it all together. Everyone gets in. Aya and Spot are there with complete data. Jolie is there with a name but an NLL migration. And 1735 is there with migration data but an NLL name. It gives you the complete chaotic reality of the data set.
Okay, so joins are all about stitching tables together side by side to attach new attributes, like you're attaching a distance to a name. But wait, how is a set different from a join? Because I know SQL also uses sets, but I'm trying to picture why we'd need them if we already have these powerful join commands.
It's a great question, and the distinction is really crucial. As you said, a join stitches tables side by side to add new columns of information. A set, on the other hand, is about stacking rows top to bottom.
Top to bottom. Okay.
Yeah, you aren't trying to attach new data. You're trying to combine two identical types of lists. When we talk about sets in SQL, we're basically talking about Venn diagrams.
Okay, let's go back to our library to visualize this. Imagine a giant circle representing a list of authors and another overlapping circle representing a list of translators.
Perfect. So SQL can perform operations on these entire circles at once. Let's say you want to find people who are both authors and translators. You use a command called intersect. It scans both lists and only returns the overlapping center of the Venn diagram.
Okay, so just the overlap.
Right. Now, let's say you want a massive master list of everyone who is either an author or a translator. You use union. It literally stacks one list on top of the other, slamming both circles together and removing any duplicates.
And what if I want the purists? Like, I only want to see authors who have absolutely never translated a book in their lives.
Then you use except petit. You tell the database, give me the authors except the translators. It takes the author circle and carves out the entire section that overlaps with translators.
I see why that works for a computer, and it's elegant logic. But let me stop you there, because it sounds like a nightmare for a human trying to read the raw output.
What do you mean?
Well, if I use all these sets and join-ons, I might end up with a list of 10,000 rows. Having 10,000 individual 4-star and 5-star ratings for a book is great for a server, but my human brain can't process that. I just want to know if the book is good or not. Like, how do we make this data actually useful for a person?
This is the ultimate so what of databases. Raw data is useless without synthesis. This is where we group the data, using commands like groupie by and having.
Group BY?
Yeah, think back to the book ratings we discussed earlier, where the foreign keys were dropping into the invisible bucket. Book ID 1 didn't just have one rating right, it had individual rows with ratings of 1, 2, 2, 4, 3.
Right. 5 separate rows.
Using the group by Y command, the database takes all those individual rows that share book ID 1, does the math behind the scenes, and collapses them into a single, understandable average, which is 2.4.
Well, that's so much easier to read.
Exactly. It does the same for book ID 43, collapsing its dozens of ratings into an average of 3.67.
It basically takes the ocean of data and boils it down into a single drop of insight.
That's beautifully put. And once it's grouped and averaged, you can use the halving clause to filter the results of that math. You can tell the database only show me books having an average rating above 3.0.
Oh, so it filters out all the noise.
Right. It ignores the poorly rated books entirely and only serves you the high-quality results.
I really want to make sure everyone listening realizes how directly this connects to our daily routines. Like every single time you are on a web store like Amazon, and you click that little button that says sort by highest rated or only show items with 4 stars and up, you aren't just clicking a simple link.
You're not.
You're literally triggering a massive group BBY and having operation under the hood. You're commanding a database somewhere in the world to instantly turn millions of raw, chaotic numbers into actionable human insight.
It's happening constantly, translating raw chaos into human meaning in milliseconds.
Hmm.
It really is the engine of the digital age.
It is absolutely incredible when you pull back the curtain. Well, to summarize our journey today, we've gone from standing in a messy, chaotic library, trying to figure out how to organize reality with entity relationship diagrams and absolute primary keys.
We really covered a lot of ground.
We did. We've nested Matryoshka subqueries sequentially inside of each other just to track down Olga Tokarczuk. We've traveled to the Pacific coast to stitch sea lion tracking data together with the VIP bouncers of full outer joins. And finally, we've learned how sets and aggregation take massive, unreadable lists of data and group them into single digestible numbers.
It is a beautiful, highly logical system, but I do want to leave you with one final, lingering idea to mull over.
Right on us.
We've seen how cleanly and elegantly relational databases can structure books, publishers, and even migrating sea lions. But remember that today, you are an entity in thousands of these databases.
Oh, wow, yeah.
Your actions, your purchases, your habits, your physical location, they are all being joined, grouped, and analyzed by primary keys that you have never even seen. So the ultimate question is, when human behavior is forced into the strict logical relationships of one-to-many and inner joins, what nuances of your life get left out as an NUL value?
Wow. That is definitely a heavy thought to chew on the next time you leave a star rating or click accept cookies. Thank you for joining us on this deep dive into the architecture of our world. Keep asking questions, keep looking for that hidden logic behind the screens you use every day, and we'll see you next time.